In this lecture, and then the following one, we're going to talk about parallel imaging. Parallel imaging is the technique of using multiple receiver coils placed around the body, each of which is connected to a separate receiver channel, to receive signals in MR, to try to increase the signal sensitivity for higher SNR, and also to enable scan acceleration by complementing conventional gradient encoding using the encoding provided by the RF coils. Today, though, specifically, we're going to talk about the reconstruction of fully sampled images from multiple coils, and then we'll start talking about the reconstruction of undersampled data using the sense technique in the image domain. Okay, so we'll start off by defining what it means to reconstruct an image from multiple coils. So this problem was most significantly first studied by Pete Romer at GE back in 1990. So here's an illustration. So we have the body here, that's the sort of oval-shaped guy here, and then we place an RF coil next to it. It's essentially a loop of wire. Okay, so this is the coil here. And this guy is going to have a sensitivity. It's going to be most sensitive to signals right next to it because it's a lot smaller than the body. So it's going to be much more sensitive to signals right next to it coming from the body. And we define each coil as having this unique amplitude and phase sensitivity, which we call C sub L of x. Each one has a unique amplitude and phase sensitivity. That is its sensitivity when it's receiving signals from the body. Okay? And so here we call this C sub L of x. It's a complex number that depends on space, and we have one of them for each channel, for each coil that we're using. Sometimes people interchangeably use the term channel for received coils. And so what we do if we want to cover the entire body is we place a bunch of these individual coils around the body such that we get sensitivity to signal everywhere. So then the question is, how do we reconstruct an image of the entire body from all of these individual coil images? Now, invariably, the coils are going to be electromagnetically coupled, meaning that they are going to receive some of the same signal, and not only some of the same signal, but also some of their noise. So their noise is going to be correlated. That means that the expectation of the noise between two channels is not going to be an identity matrix in general. And so the phi matrix here, which is the noise correlation matrix, is going to be size L by L, again where capital L here is the number of received coils that you have. And our model here is that the measured signal from a given coil, M sub L of x, this is the measured signal, is equal to the sensitivity of that coil. That's the sensitivity, and this is the signal at the voxel x, sensitivity times that signal, plus some noise. And so the question is, these are the images we can reconstruct for each coil, right? Reconstruction from each individual coil is the same as any other reconstruction. We just take a Fourier transform or a gridding, whatever it is, depending on the acquisition that we did. So given this signal from each individual coil, how can we reconstruct M of x, an image of the entire body? So what we have here is L measurements of each voxel, right? Because each voxel is in every coil's image, right? We have coil 1 received this voxel, coil 2 received this voxel, and coil L also received this voxel. And we need to figure out how we're going to stitch these images together. So for a particular voxel at xp, we have the following system of equations. We have that the individual coil images are equal to the true value of the signal there multiplied by each coil sensitivity, and then added to that the noise from each coil. Or in matrix vector notation, we can stack these up into a single matrix M sub S, where M sub S is the L by 1 measurement matrix, or measurement vector. The C here is an L by 1 sensitivity vector. This is a 1 by 1 pixel, right? It's a scalar value. And then we have our L by 1 noise vector. The noise in this vector n is normally distributed, right? So it's complex valued noise, So you consider it to be an independent real independent real and imaginary parts. We divide each by root 2 to get a variance of 1, a normalized variance of 1. And it turns out then that the minimum variance estimate, the minimum variance estimate of m of xp is given by C Hermitian psi inverse C inverse C Hermitian psi inverse m sub s of xp. Right? So we take these measurements that we have, and then we multiply them by this overall matrix, this overall vector actually. So it turns out it's a vector. This guy is 1 by L, and this guy is a scalar, it's 1 by 1. On Phillips scanners, such as we have at Vanderbilt, this is called the clear method, the clear reconstruction method. What they do on the Phillips system is they measure the noise correlation matrix across the coils, and they measure the sensitivity values, and so that gives them everything they need to get this coil combination vector that they multiply into the individual coil images. The variance of this estimate is equal to C transpose psi inverse times C, which is a scalar, right? It's a single voxel, so it has to have a scalar variance. In the special case where we have the noise correlation matrix is an identity, which means that the noise is completely uncorrelated between the coils, which further means that they must be completely decoupled. Then, if we have that condition in the ideal case where we're going to get an identity matrix for the noise covariance, then our estimate simplifies. So it's originally C Hermitian times sigma squared I inverse times C, right? This is substituting the definition of psi into the expression that we had on the previous slide, times C Hermitian sigma squared I inverse times m sub s of xp. Again, m sub s of xp is the vector of individual coil values at this spatial location. Because we have an identity matrix for psi, though, this simplifies to just C Hermitian C inverse times C Hermitian times m sub s of xp, right? Because we end up having sigma squared in the denominator of the denominator, so it moves up into the numerator, and then we have a sigma squared in the denominator, so those two sigma squareds cancel. So this simplifies in that step, and then we can give an analytic, a more detailed expression for it, where we have 1 over the sum of C sub L of xp magnitude squared times sum over L C sub L complex conjugate of xp times m sub s sub L of xp. Okay? So what this is called is a weighted average combination of the individual coil signals. And in this combination, what we get out of this is a phase-corrected signal, because we're multiplying each individual coil signal by the complex conjugate of its sensitivity, so we're removing the phase from the coil sensitivity. And then we're also removing the weighting of the coil sensitivities by dividing by their sum of squares. Now, often we not only don't know what the noise correlation matrix is, but we might not know what C sub L is, what the sensitivities are, C sub L of X. However, the images that we get from each coil, m sub L of X, is equal to the true image times the sensitivity. So m sub L of X already has some weighting implicitly of C sub L of X. So one way to do this, to approximate this solution, to approximate having C sub L of X, is to do a sum of squares combination. So we call this SOS. Sum of squares. And this is given by square root of the sum over coils of each individual coil's image times its own complex conjugate. And if we write this out, then what we get is sum over L C sub L, squared times m squared magnitude, which is equal to magnitude m squared, right? Because that comes out of the, just magnitude m, that comes out of the summation, times square root of the sum over c sub L magnitude squared. And this guy is approximately m hat of xp amplitude if the sum of squared combination of the sensitivities is approximately 1. So if is approximately 1. Right? So if you have good coverage everywhere and relatively uniform coverage everywhere with the sensitivities, you can get away with this. So this still also phase corrects because we implicitly are multiplying by the complex conjugate of C, and it weights the measurements. The square root, taking the square root here approximately fixes the weighting, but it does leave some shading if there's residual, if the coil sensitivities are not approximately equal to 1 when you take their sum of squares. But for an SNR greater than about 20, which is not too hard to reach usually in MR, this coil combination is within about 10% of the optimal solution, which was a result derived by Romer. So this is long thought to be adequate. Though nowadays most scanners are able to get the sensitivities and do the more sophisticated combination. So now let's switch gears and go further into the accelerated MR imaging with SENSE. So the basic idea of parallel imaging methods such as SENSE is that coil elements provide some localization of the signal. That is, the sensitivities that we have are most sensitive to signal that is right next to them, and so you can theoretically encode a smaller field of view. So this allows, the fact that they are most sensitive to spatial locations near them allows you to, it turns out, allows you to undersample k-space, that is, skip points in k-space that you would normally acquire, which would produce aliasing, of course. But then you can sort out, it turns out that if you know what something about the coil sensitivities, you can sort out the aliasing in the reconstruction. And the consequence of this is really profound in that the gradient encoding that we typically have to do a full k-space encoding, which takes a lot of time, can be traded for sensitivity encoding, which is instantaneous. It just instantaneously multiplies into the image signal. And this results in huge time savings. Another way to think about it, which is the basis for frequency or k-space domain approaches such as GRAPPA or SMASH, is that the sensitivity multiplication in the image domain is equivalent to a convolution, of course, in the frequency domain. And what that means is that each coil picks up image data from not just the point that is exactly visited by the k-space trajectory, but also from a neighborhood around each k-space location, right? Kind of like in the type 2 FFT, right? We multiply, we convolve our Cartesian k-space with a kernel, and we kind of, that weighted data gets pulled up into the data point. That is essentially what's happening when you have multiple localized receive channels as well, but now instead of a Kaiser-Bessel kernel, for example, we have the Fourier transform of the coil sensitivity. And it turns out then that if each coil has a unique known sensitivity, we can reduce sampling density in k-space, right, which results in having to sample fewer locations, and approximately blur out the data that we did acquire in k-space to fill it back in. And so here we're going to focus on two specific parallel imaging methods, which are the two most widely used approaches to parallel imaging. The first is SENSE, which is optimal if you know the coil sensitivities well. It's easy to visualize and easy to analyze, and so that's why we're going to talk about it first. The other method is called GRAPPA, which works in the frequency domain. It's auto-calibrating in that you can get the received sensitivities from a certain region of k-space that is fully sampled, and it can be quite robust then to effects like motion that might occur between when you acquired the received sensitivities and when you actually did the reconstruction, got the accelerated data. Okay, so first let's talk about SENSE, and specifically we'll talk about 2D Fourier transform SENSE, or SENSE applied to 2D FT scans where you're doing rectilinear sampling of k-space. So let's say that we have capital L receive coils, as discussed before, and we undersample k-space by a factor of 2. So here I've illustrated an object here, that's the oval, and we've got a coil up here and a coil down here. And this is the entire field of view that we need to resolve in order to not have the object alias on top of itself. Now, so here's the fully encoded case where we would be able to resolve these two voxels in here, x1 and x2. Now, if we undersample k-space by a factor of 2, then the object is going to fold back onto itself, right? This top end is going to come back up here, and this bottom end is going to come up here. And so then if you get two images of it, you're going to have coil 1, an undersampled image from coil 1, where we have these two voxels aliasing directly on top of each other. And then we're also going to have another image from coil 2. Now these two images are going to have different receive sensitivity weightings on them. So what happens here when we undersample, k-space by a factor of 2 is that these two voxels and every pair of voxels will alias on top of each other. So they alias to a point in the factor 2 undersampled image, which we call xp. And mathematically, the signal that we get in the accelerated or aliased image at this point xp is equal to a weighted sum of the original signals at the two voxels. So the signal that we get in coil L at this location xp in the aliased image is equal to coil L's sensitivity at voxel x1 times the true signal at voxel x1 plus coil L's sensitivity at voxel x2 times the true signal at x2. So what we have is L measurements at this point xp, each with different sensitivities, right? Because we acquired the undersampled image with capital L separate coils. So you can start to maybe get some hints here about how we're going to have enough equations to be able to get back the original signals at the two voxels that overlap, that aliased onto each other. So we can stack up all these different measurements across the coils. We have M1 of XP up to ML of XP. Again, this is the voxel values at alias location, at undersampled image location XP across all the coils. So this is the vector of aliased image pixels for each coil. And this guy is equal to the source voxels, M of x1, M of x2. Again, these are what we're trying to recover, but they're going to be mixed together by the weightings of the sensitivities. And specifically, that matrix is going to be C1 of x1, C1 of x2, all the way down to CL of x1, CL of x2, right? So this is an L by 2 matrix. This is a length 2 vector, and then we have the noise. So this matrix contains the sensitivities at the source voxels, and we have that multiplying into the source voxels. And finally, we're going to have additive noise, N1 to N sub L. In matrix vector form then, we can write this, we call this vector M sub S of XP, this matrix is called C, this vector is M, and this vector is N. Okay, so specifically this guy is L by 1, this guy is L by 2, this guy is 2 by 1, and this guy is L by 1. So it turns out that the same minimum variance solution that we had in the coil combination case applies here as well. So that is, what we want to use here is C Hermitian psi inverse C inverse C Hermitian psi inverse M sub S of XP. The primary difference here is that the dimensions of the matrices and vectors change. So now we're solving for two separate voxels, not just one as we were before. This matrix is now 2 by 2 instead of a scalar. This this matrix here is 2 by L, and this still is L by 1. And we can further derive the covariance matrix here, which is has elements C Hermitian psi inverse C inverse JJ. And we'll talk more about that later. So, if we have enough coils with sufficiently distinct sensitivities, L-aliased reconstructions, separate image reconstructions can be unfolded to resolve the two image pixels that aliased on top of each other. And so, if we had an n by n image undersampled by factor 2, we would have to solve separately n over 2 by n versions of this problem, where these are all 2 by 2 inverse systems. For larger undersamplings or accelerations of r, we would solve, in general, n over r by n separate problems, where the size of the problem is r by r. So we have many small problems to solve, each of which can be solved very quickly. But the question is, how large can capital R be? That is the acceleration factor, or it's also equal to the number of voxels that are aliased on top of each other. So in the next lecture, we're going to talk about the S&R cost of parallel imaging, and we'll also talk, which is quantified in terms of what's called G factor.